You can stay in here, I don't care. Okay, so so here is the theorem. This is the Graham-Schmidt process. So this is theorem 5.15. Okay. Okay, so it says, oh gosh, let this set x1, xk be a basis for a subspace W of Rn, and define the following. So we'll say V1 is x1, so we're just going to start with x1, and then V2 is going to be x2 minus the projection of x2 onto V1. So you recognize this part here as the projection. I think I was using blue for the projection earlier. So if we take the vector minus the projection onto the previous vector, then what we're left with is the orthogonal part of x2. So then V3 is going to be more of the same. Well, I want V3 to be orthogonal to x1 and x2. So V3 is going to be x3 minus, we want to subtract off the part that's in the direction of V1. And then we want to subtract off the part that is in the direction of V2. So these are dot products here, sorry. I didn't draw the dot, they're very good. They're dot products. So we're subtracting off the part that is in the direction of V1 and the part that's in the direction of V2. And so what's left over will be orthogonal to both V1 and V2. And we're just going to continue in this manner. So we'll just do dot, dot, dot. So VK is going to be XK minus, we're going to subtract off the part that's in the direction of V1. And we'll keep subtracting off all those parts until we subtract off the part that is in the direction of VK minus 1. So as you can see, you're just going to take that vector and subtract off the parts that are in the direction of all the other vectors, and then what's left over will be orthogonal to the rest of the set. So then, for each I equal 1 through k, we have that V1 through VK, or V1 through VI, is an orthogonal basis for WI. In particular, V1 through VK is an orthogonal basis for W. And so those guys are just orthogonal. Now, they're not necessarily unit vectors, but we can make them an orthonormal basis if we just scale them all by by 1 over their magnitude. Then I could end up with an orthonormal basis. But that's the process. So we're going to start with the first vector, and then we'll take the component of the second vector that's perpendicular to the first one, and then the component of the third one that's perpendicular to the first two. So that's the process. Let's do a little example. And we'll construct an orthogonal basis, starting with a basis that is not orthogonal. Okay, so apply the Graham-Schmidt process to construct an orthogonal basis for the subspace W equals the span of x1, x2, x3, where x1 is 1 minus 1 minus 1, 1. x2 is 2, 1, 0, 1. x3 is 2, 2, 1, 2. Okay. And so, so I'm assuming since they're asking us to use the Gram-Schmidt process that these guys are already not orthogonal to one another. I'm just going to check real quick just so that you can see that these guys are not actually orthogonal. So if I do x1 dot x2, what am I going to get? I'm going to get 2 minus 1 plus 0 plus 1. 2 minus 1 plus 0 plus 1. So that gives me 2. And so I can see x1 and x2 are not orthogonal to one another because their dot product is not 0. So, so they're not orthogonal. Now, you don't have to check. I just wanted to point out that we can check. Maybe we're given a basis that actually is orthogonal. That would be great. But in this case, no. So what we want to do is we're going to start by letting my V1 be x1. And so then V2 is going to be x2 minus the orthogonal, the bit that is projected onto x1. So it's going to be x1 dot x2 over x1 dot x1. Oh, I guess I should be using V1. But V1 is x1, so anyway. V1. Okay, so x2 I can write out is 2, 1, 0, 1. And then I want to subtract off. Okay, so if I do V1 dot x2, that's going to be, that's the same as x1 dot x2. So I'm going to get, I'll just write it all out. So 1 times 2, oh, I already did it. So I'm going to get 2 minus 1 plus 0 plus 1 over. If I do V1 dot V1, I'm going to get 1 plus 1 plus 1 plus 1. And I'm going to multiply that by x2, which is 2, 1, 0, 1. Okay, so this gives me, okay, yeah, that's what I want. Oh, no, wait, I want to multiply by x1, which is, sorry. It's multiplied by V1, which is x1. So 1 minus 1 minus 1, 1. Sorry, got excited there. Okay. So I get 2, 1, 0, 1. And then I'm going to say minus 1/2 times 1 minus 1 minus 1, 1. And so this is going to give us, okay, so let's do this. So I'll have 2 minus 1/2, so I'll have 1.5. And then I'll have 1 minus negative 1/2, so 1 plus 1/2. So that's 1.5. And then I'll have 0 plus 1/2, so that's 0.5. And then I'll have 1 minus 1/2. So that'll be 0.5. Okay, so that is my first one. And so next, I'm going to say V3 is going to be x3 minus, then I want to do, I want to subtract off the bit that is in the direction of x1. So I'll do V1 dot x3 over V1 dot V1, V1, minus, I'm going to subtract off the bit that's in the direction of V2. So V2 dot x3 over V2 dot V2, V2. Okay, perfect. All right, so let's work that out. So that's going to be, okay, so x3 is this guy, 2, 2, 1, 2. And I want to subtract off, okay, if I do v1 dot x3, so v1 is that guy, dot x3. So I'm going to get 2 plus, 2 minus 2, minus 1 plus 2. So over, and then v1 dot v1, again, is 4. 1 plus 1 plus 1 plus 1. Okay, so, and then that is multiplied by v1, which is 1 minus 1 minus 1, 1. Okay, and then I'm going to subtract off. So it's going to be v2 dot x3. So v2 is over here, 1.5, 1.5, 0.5, 0.5. So v2 needs to be multiplied by x3. So 1.5 times 2, that's 3, plus 3, plus 1 times 0.5 is 0.5, plus 0.5 times 2 is 1. And that's over v2 dot v2. So it'll be 1.5 times 1.5, which is 2.25, plus 0.5 times 0.5 is 0.25. And all of that is multiplied by the vector v2, which is 1.5, 1.5, 0.5, 0.5. Okay, so let's get all this together. So I have 2, 2, 1, 2. Minus, okay, so that simplifies to 2 minus 1, so with 1/4 times 1 minus 1 minus 1, 1. And then a minus, and then here I'm going to have 7.5 over, what does that add up to? 5? I think so. So 7.5 over 5. Which ends up being 1.5. Okay, and then that's multiplied by 1.5, 1.5, 0.5, 0.5. Okay, and so then we get, okay, let's add this all up. So I'm going to get 2 minus 1/4. Minus 1.5 times 1.5. So I get negative 0.5 for the first one. And then for the second one, I'm going to get 2 plus 1/4 minus 1.5 times 1.5. So that gives me 0. And then for the third one, I get 1 plus 1/4 minus 1.5 times 0.5. So I get 0.5. And then for the last one, I'm going to get 2 minus 1/4 minus 1.5 times 0.5. So I get 1 in the bottom one. Okay, and so now I have my bases. So my v1, v2, v3 is equal to this set. So v1 is x1, 1 minus 1 minus 1, 1. v2 is that guy, 1.5, 1.5, 0.5, 0.5. And then v3 was negative 0.5, 0, 0.5, 1. Now, are these guys, let's just check. Can we check to see if these guys are orthogonal? Because we did this whole process to show they're orthogonal, but let's just show it. If I did v1 dot v2, what do I get? Well, I'm going to get 1.5 minus 1.5 minus 0.5 plus 0.5. So that adds to 0. If I do v1 times v3 dot v3, I get negative 0.5, 0, plus 0, minus 0.5 plus 1, and that adds to 0. if I do v1.v2, or sorry, v3.v2, I get negative, so 1.5 times 0.5 is 0.75. So I get negative 0.75 plus 0 plus 0.25 plus 0.5, and that gives me 0. So I can see that this basis is orthogonal. I checked it. It's orthogonal, so any of those vectors dotted with each other gives us 0. But it's not orthonormal. So to make it orthonormal, I need to scale each vector to make them unit vectors by 1 over their magnitude. So 1 over the magnitude is what I need to scale by. So we'll call them Q1 is going to be the scaled version of this. So this is going to be 1 over the square root of 1 plus 1 plus 1 plus 1 multiplied by 1 minus 1 minus 1, 1. So the square root of 4 is 2, so it's going to be 1/2 minus 1/2 minus 1/2, 1/2. And that is now a unit vector. And Q2 is going to be 1 over the square root of, oh gosh, okay. So I'll have 1.5 squared plus 1.5 squared plus 0.5 squared plus 0.5 squared. And so what does that all add up to? Oh, and it's going to be multiplied by V2. Okay, so if I do that, 1.5 squared plus 1.5 squared plus 0.5 squared plus 0.5 squared, and that gives me 5. So it's going to be 1 over the square root of 5 times the vector 1.5, 1.5, 0.5, 0.5. So that gives us 1.5 over square root of 5, 1.5 over square root of 5, 0.5 over square root of 5. Sorry, it's getting ugly. 0.5 over square root of 5. Yeah, so there's my vector. That's a unit vector now. Last one. Okay, this is getting a little bit boring. So Q3 is going to be 1 over the square root of negative 0.5 squared plus 0 squared plus 0.5 squared plus 1 squared. So that's going to give multiply that by the vector 0, 0.5, 1. Okay. And so that's going to be, so I get 0.25 plus 0.25 plus 1. So square root of 1.5. Okay. And so that gives us negative 0.5 over square root of 1.5, 0 over square root of 1, so which is just 0. And then I'll have 0.5 over square root of 1.5, and then 1 over square root of 1.5. Okay, and that is the example that we have there. And so that's pretty much all that you need to get through the homework.